Basically, what we're going to do here are things off these worksheets. Once again, these are the types and style of problems that you might see on the exam to do with chapter 17-ish. Okay? I'm going to start off with what we've already said here, and that is just our review of nomenclature. The exam will have nomenclature in two formats. It will have simple, give me the name. It will have do the reaction and give me the name. Okay? Remember, alcohols end in OL. You want to give the alcohol, the hydroxyl group, the lowest number. And we want to arrange substituents alphabetically.
So, Dr. Young, so wherever the alcohol is, start with their number 1, right?
No, no, no. It has to have the lowest number. Not number 1, but the lowest possible on the chain. So if we have this, look at this guy. Our parent here is going to be 1, 2, 3, 4 carbons. The alcohol must be on the parent chain. So our parent is going to look like this. Now we have to number this thing so that the hydroxyl group gets the lowest number. If we had a tie in this molecule, we would go for the lowest number overall. But here, our hydroxyl group would be number 2. If we started here, here it would be 3. Therefore, that's going to be carbon 1, 2, 3, and 4. So this is a bromo alcohol, right?
Bromo, it's a 1 bromo butanol.
We are a 4 carbon, so that's a bute. It's a 1 bromo bute, and it's a 2 alcohol. We could write it something like 1 bromo 2 methyl 2 butanol. Or remember, you can move the 2 down here in front of the all. This is actually the latest version of what our UPAC likes. I think it breaks the name up a little bit too much. This is still entirely acceptable. Of course, if you put either one, that would work. The thing that I look for in a name is that it's not ambiguous. The name must absolutely describe the compound, no ambiguity. So, 1 bromo 2 methyl 2 butanol. Okay. Here I have 3 names. We'll do this backwards. Instead of giving you the compound and asking you to draw or name it, here I'm going to give you the name and ask you to draw the compound. Cyclohexane is our parent, 6-membered ring. We have 2 hydroxyl groups. They are at carbons 1 and 3. You must somehow show their stereochemistry as cis. Now you could do that with a chair if you drew the 2 either both axial or both equatorial. No, I'm sorry, axial equatorial. So axial equatorial, or we could use wedges and simply do it this way. So again, if you drew a chair, you would have to draw them axial equatorial. If you use wedge bonds, this will work. All right, our next compound. Our parent's a pent, 5 carbons. Draw 5 carbons. It's a 1-pentanol, so in carbon 1 you put an OH group. You count down the chain to carbon number 4, and you stick on a phenyl group. Here's a 4-carbon chain. Have a hydroxyl group on carbon 1. Or a 5-carbon chain. Hydroxyl group on carbon 1, phenyl group on carbon 4. Our next compound, again, is a cyclohexane parent. It's a cyclohexanol. So by definition, the ol is going to be attached to carbon number 1. Relative to the alcohol, right, carbon number 4, we have 2 methyl groups. Therefore, you're dealing with something like this.
Slow down for a second, go back. Sorry, it's a dumb question maybe, just because I don't know it. On the second one, why does it look like there's an extra methyl on the 4?
Well, we have a, let's go back here. We have a pent, right?
Yeah.
So 1, 2, 3, 4, 5 carbons. I drew it down, but you could draw it up, doesn't matter. Okay? 5 carbons. It's a 1-pentanol, so you go to carbon number 1 and you put your OH group.
Okay.
Then you count down to carbon 4. 1, 2, 3, 4, and put a phenyl.
So it doesn't really.
A phenol has a line to it, that's it.
Well, you can draw the phenol anywhere then.
Yep, up, down, sideways. Remember, these are all free rotations.
Well, you can draw it like on the 3rd carbon. or
No,
the second
it
carbon.
has to be on carbon 4. 4 phenyl. So 1, 2, 3, 4. Has to be on carbon 4. All right, again, we have a pentanol. It's a 1-pentanol. So you draw your 5-carbon chain. On carbon number 1, you put the hydroxyl group. You count down to carbon 3. You put a methyl. Count to carbon 4. Put another methyl. And it looks like this. 1, 2, 3, 4, 5. 5 carbons. Alcohol on carbon 1. Methyls on 3 and 4. Our next one is a cyclopentane. So our parent is cyclopentane. We have hydroxyl groups on carbons 1 and 2, and they are cis. All you have to do is draw your cyclopentane. You need to show stereochemistry of some sort so that the hydroxyl groups look like they're cis, and that will do. How would you make this compound? You would take cyclopentene and react it with potassium permanganate. Remember, that gives you a cis 1,2-diol. Our last one, 2-phenyl ethanol. All right, ethanol is a 2-carbon chunk, isn't it? It must have the OH group attached to one end or the other. So this is ethanol. By definition, this must be carbon 1. That's carbon 2. On carbon 2, we need a phenyl group. This is ethanol. Attached to carbon 2, we have a phenyl group. Two more simple ones here. This is a pentanol. So we have 5 carbons in our chain. You count down to carbon number 3. You put the OH group. Go back to carbon number 2. You put the methyl group. And it looks like this. Carbon 1, 2, 3, 4, 5. Hydroxyl group on carbon 3. Methyl group on carbon 2. And our last one, we're also dealing with a pentanol. So we start off with a 5-carbon chain. On carbon number 2, we're going to put our hydroxyl group. On carbon number 4, we're going to stick a methyl group. And it should look like this. What's the relationship between these two compounds?
Or Phenols. Oh, it's called, not stereo, it's the other one.
Right, it's not stereo. They are constitutional isomers, aren't they? They are both methyl pentanols, but their constitution, that is the arrangement of the constituents, is different. You remember that. All right, reactions that yield alcohols. Going back to alkenes, simple acid catalyzed hydration. We know that acid catalyzed hydration is going to give us a carbocation intermediate with rearrangement and Markovnikov
Dr.
regiochemistry.
Young, you're skipping something. How are we following this? Where is it?
Well, this isn't a problem, this is just a discussion.
Oh, okay, sorry.
You already know this. Whenever you see this reaction, these are the words that go in your mind. Carbocation intermediate, rearrangement, Markovnikov. That's what you think. A more civilized way, mercuric acetate. No rearrangement, but still Markovnikov. That's from chapter 8. You know those. Again from chapter 8. We can get anti-Markovnikov alcohols from hydroboration oxidation. Chapter 8. Anti-Markovnikov. And finally, as we just saw in our previous slides, an alkene with permanganate gives a cis 1,2-diol. Well, that's chapter 8. You know that. You had exam 2. You're happy with that, right? Right. In chapter 17, we looked at new reactions. Reduction, aldehydes and ketones. Aldehydes with lithyl or borohydride gives primary. Ketones give secondary alcohols. We know that Grignards with a aldehyde will give a secondary alcohol. Grignard with a ketone will give a tertiary alcohol. Chapter 17 again. Oh, okay. Here it is in writing. aldehydes and ketones, Grignards, again, secondary and tertiary alcohols. Conversion to alkyl halides, PBr3. What do we remember? We remember that we have a phosphide ester, that this is an SN2 displacement, and therefore it goes with inversion of stereochemistry. That's what we remember when we see this reaction. We also know we can do this with thionyl chloride. In pyridine, we will get a chlorosulfide ester. Chlorosulfide ester, same thing. Chloride attacks, this leaves SN2 process with inversion. When you see thionyl chloride pyridine, you think alkyl chloride inversion. The cute thing is, if we do this in a nonpolar solvent, we get an SNI mechanism, and that gives us retention of configuration.
Non-polar solvent, got it.
All right. If we have an alcohol, we can convert it to an alkene with strong acid. This is an ugly reaction, carbocation intermediate rearrangement. A much more civilized way to do it is with POCl3 and pyridine. It's a nice, happy E2 reaction. A chlorophosphate ester. Pyridines are base. Again, no rearrangement, no issues. Chapter 17, we also talked about oxidation. The mildest form of oxidation was PCC and dichloromethane. Primary alcohols to aldehydes. Also works with secondary alcohols to ketones. Very nice reagent. Just remember PCC. Very gentle. Any questions? All right, let's look at a set of reactions here. This is off your sheet. Very quickly, jot down the products of all of these guys. Again, pretend this is an exam. On your exam, you will have at least one page, maybe two, of reactions that will look just like the set you're doing now. So, 8 or 9 reactions on a page. Only difference is on the exam, I'm not standing up here to do the answers for you.
And then 8 or 9 of the alkenes. One page of this, and then 8 or 9 of the alkenes.
Yep, probably, or all kinds. Now there will be alkene reactions too, because those yield alcohols. So if we're dealing with alcohols, it'll be a mix. All right, PBr3, when we see that, what do we think? We think intermediate phosphide ester, SN2 chemistry, inversion, wind up with an alkyl bromide. We don't have stereochemistry here, so anything you drew would have worked. Just a bromocyclohexane. Now our next one, thionyl chloride impurity. Once again we say to ourselves, alkyl chloride with inversion. That's important because this is a chiral center, isn't it?
Yeah. Yes.
Yes, it is. All right. So what we have to do is get rid of our alcohol. We have to substitute a chlorine. And we have to show inversion. On the exam, you would have to do that. Simplest way to do that, remember, all you have to do is swap any two groups. And that gives you inversion. So I'm going to just put the chlorine down here where the hydroxyl was. And I'm going to move my methyl to the back. And that puts the hydrogen in the front. Now, just in case you don't see the hydrogens, there they are. Starts off with hydrogen in the back, wind up with the hydrogen in the front, methyl in the front, methyl in the back. But you should just be able to do this in your head. PBr3, once again we have alcohol to alkyl bromide. We have inversion. This is not a stereocenter. Therefore, we simply draw the bromo dimethyl cyclohexane. Our next set. We have an alcohol. We have POCO3 and pyridine. What do we remember about that?
No rearrangement E2.
E2, no rearrangement, nice, clean, happy reaction. We're going to lose this alcohol from this carbon. Because there's no rearrangement, we wind up with this alkene. These are the two carbons of the alkene. Lose the OH and an H. Once again, PBr3. We have a chiral center here. Going to convert that to an alkyl bromide, and we have to show inversion. All we have to do, since our alcohol is coming towards us, is draw something like this with the bromine going back. That clearly represents inversion of configuration. Our next guy here, simple secondary alcohol. We have HCl and ether. This is going to protonate the alcohol. It's going to leave. It's going to give a carbocation, and we will wind up with an alkene. That's okay, really, because we're going to get a benzyl carbocation, aren't we? So it's going to be an E1 reaction. Product is simply styrene. All right, pay particular attention to this next guy. Our new oxidizing reagent, PCC. You remember, PCC will take primary alcohols to aldehydes, secondary alcohols to ketones. When you draw the product, remember, all you're going to do is convert the OH group into a carbonyl, right? That's all you have to do. This has a hydrogen attached that we don't show. The product is simply the aldehyde. Now our last one here. We have a primary alcohol, and we have CrO3 in water. That's our powerful oxidizing conditions. That's going to take the alcohol all the way to the carboxylic acid. In reality, it first goes to the aldehyde, but the aldehyde is instantly oxidized to the carboxylic acid. So, here where we have the oxygen attached, that's going to be a carbonyl still. But it's going to be a carboxylic acid, so it has an OH attached. And it looks like that. This is the carbon that was the OH. We oxidized the OH to a carbonyl and made it an acid. PCC would stop at the aldehyde. Just chromate itself goes to the acid. All right, next, the third sheet. I promised you you would see reactions like this on the exam, and you will. I want you to take 2 carbonyl compounds and 2 Grignard reagents, and I want you to make this secondary alcohol. Well, let's do this our standard way so we don't panic here. We're going to take our alcohol and we're going to cleave it on one side, like this, and we're going to identify the Grignard reagent and the carbonyl compound. Carbonyl half is the one with the oxygen, isn't it? We're looking at benzene ring, and this was a carbonyl carbon with a hydrogen attached. It was an aldehyde because it's a secondary alcohol now. Therefore, the only one that's going to work is benzaldehyde. Now, draw me the structure of the Grignard reagent that you need.
Oh, so it's not 2 of those.
Nope, nope,
Oh.
nope. You come up with a Grignard now. The Grignard is 3 carbons, 1, 2, 3. This is our nucleophilic carbon, so something like isopropyl methyl or magnesium bromide will work. All right, do the other side. We're going to split here. Draw me or pick out the appropriate carbonyl compound and draw me the appropriate Grignard. It's a secondary alcohol, so we're looking up top for an aldehyde, aren't we? The aldehyde must have this isopropyl group attached to one side. As we look at our selection here, this aldehyde seems to work.
There's two answers for each one.
And our Grignard is simply the other half. That's this stuff. This is a phenyl group, so it is just phenyl magnesium bromide. Again, we have a secondary alcohol. That means we're dealing with an aldehyde. Take it and split it on both sides. Pick out your two carbonyl compounds. If we split on this side, our carbonyl compound is an aldehyde and it has a benzene ring. That is benzaldehyde up here. Our Grignard reagent must have 1, 2, 3 carbons for magnesium bromide, and a methyl group here on carbon 2. So it's this chunk, a 1, 2, 3, 4 carbon chunk, drawn like that. All right, let's split on the other side. Look up top, find your aldehyde. Again, you know it's an aldehyde because it's a secondary alcohol. The aldehyde must have a 1, 2, 3, 4 carbon parent. And in carbon 3, we must have a methyl group. From the selection, this guy up here is a methyl group. Our Grignard is simply the other half, and that is our phenyl group. See how simple this is? Don't you feel really smart? Yes. Any question on it?
Just gotta let it soak in, you know?
Again, we have a secondary alcohol. So again, we are looking for an aldehyde. Let's split on this side. Pick out your aldehyde and your Grignard. The aldehyde simply has a 2-carbon chain attached to it, attached to the carbonyl carbon. And the one up here that works, this is a ketone, it's this guy. Our Grignard is the other half. It's our isopropyl group with the Grignard attached to carbon 2. All right, split on the other side. Our carbonyl compound, again, is an aldehyde because it's secondary alcohol. It is a 3-carbon parent, methyl group in carbon 2, and the one that works is that. The other half is simply a 2-carbon chunk, isn't it? That's an ethyl group. So we want ethyl magnesium bromide. One more secondary alcohol here. Split it. Pick out the appropriate aldehyde and draw the structure of the Grignard. Polyaldehyde has a 1, 2, 3, 4 carbon parent, methyl group in carbon number 3, and it looks like that. The Grignard is simply this 1-carbon chunk. 1-carbon chunk is methyl magnesium bromide.
How do you call that again?
Well, this is a methyl group, isn't it? I just didn't put a CH3 on it. Methyl magnesium bromide. If we split on the other side, our aldehyde is a 2-carbon chunk. And our Grignard is 1, 2, 3, 4 carbons, where this is attached to our magnesiums. The aldehyde up top that works is simply acetaldehyde. The Grignard, once again, 4-carbon chunk. This was attached to the magnesium, and it looks like that.
Does the carbon chunks always work like that? You just count the carbons out, does that always work?
Yep.
Okay.
Yep, always works. Split on both sides, work out.
Do the opposite.
All right, now we have a tertiary alcohol. We can make a tertiary alcohol 2 ways. From a ketone or from an ester. Let's do the ketone. Now if you look at a tertiary alcohol, all 3 arms are the same, aren't they? So we're looking for a ketone. Where this was a carbonyl, we've added 1 group as a Grignard, and our ketone simply has an ethyl group on both sides. The ketone that works is this guy up here. All we need to do is take a 2-carbon Grignard and add it to that carbonyl carbon. The 2-carbon Grignard would be ethyl magnesium bromide. All right, the other one. We can also make a tertiary alcohol from an ester, right? Now we know that we're going to add 2 groups, 2 Grignards to our ester, right? So again, these 3 arms are the same. Let's just cut off 2 of them. These are going to come from Grignard. And whatever's left in the middle here, that was our ester. This was the carbonyl carbon of our ester, wasn't it? Attached to the carbonyl carbon, we have a 2-carbon chain. Now it's an ester, so it's attached to O something or other. But we don't care what, because we lose that. Up top, we have 2 esters to choose from. Which one would you choose? Remember, we lose the O something or other. So we lose ethoxide, we're left with a hydrogen. Here we lose methoxide, and we're left with a 2-carbon chain. This is the one we want. Our Grignard is simply a 2-carbon Grignard. So again, that's ethyl magnesium bromide, and we need 2 of them.
These are going to be on the test too? These are
Of
gonna be on the
course.
exam?
All right, let's look at this guy. Secondary alcohol, right?
Yes.
We can do that. Secondary alcohol, we're looking for an aldehyde. We're going to cut on one side, pick out our aldehyde. Carbonyl carbon of the aldehyde must be attached to a 2-carbon chunk, and therefore it must be that. The Grignard is this 2-carbon chunk. So once again, it's an ethyl group. Ethyl magnesium bromide. Now is when it gets interesting, though. Because this is symmetrical, if you cut on this side, it's exactly the same reagents, isn't it? And you don't get credit for it twice. So you got to come up with another way to make it using this stuff up top. There is one other way we know to make a secondary alcohol out of a carbonyl.
Bottom left.
It's an ester reaction again, isn't it? But the ester must be attached just to a hydrogen. That is, it must be a formate ester. Now, once again, formate. Formate is a trivial name, it's a common name. This is formic acid. This is the stuff that stings in a ant sting.
Oh, really?
Yeah. Formic acid. So a formate ester, simply this will be an OR, but it has a hydrogen attached. That's why we get a secondary alcohol, because it has a hydrogen and not an alkyl group. All right, so you look up top. Where's our formate ester? There's only one. It's this guy. We're going to add 2 moles of Grignard to our formate ester. Hydrogen survives. It's hanging off here. We don't show it. And our Grignard, 2 carbon Grignard. We need 2 of them. 2 moles of ethyl magnesium bromide. All right, let's flip back to the last 2 slides of the chapter 17 lecture, where we have the problem sets before you guys moved out. Let's just quickly look at all of these things, pretend it's a reaction sheet, and let's do these reactions. And then I'll quit, I promise. Our first reaction, we have cyclohexanone, we have sodium borohydride. We know that that is simply reduction. We're going to add hydride to the carbonyl carbon and make it into a secondary alcohol. Our next reaction we've done several times now. This is an ester reacting with a Grignard. We know we're going to add 2 moles of Grignard to it. We're going to get rid of our methoxy and never ever see it again. Carbonyl is going to be an OH, and we're going to have 2 methyl groups attached. If you took this alcohol and you put it in acidic solution, what do you think is going to happen?
Pronate?
Well, we're going to protonate this, it's going to leave, right? That's going to do it really easily. Why? Because the carbocation would be not only tertiary, but benzyl. It's called cumene. Very, very stable carbocation. All right, our last one, we have lithol, we have a carbonyl. All in the world we're doing is converting that into a secondary alcohol. The last set here. We have a secondary alcohol. We are reacting that with PCC and dichloromethane. We remember that PCC is a nice, gentle form of chromate. Very gentle, very specific. It'll take a primary alcohol to an aldehyde, a secondary alcohol to a ketone.
If there was stereochemistry, would it flip? If there was stereochemistry, would it flip?
No, because we're going from sp cubed centered to sp squared. So we would lose all stereochemistry. Grignard reaction. have an aldehyde. We're going to get a secondary alcohol, aren't we? We're going to attach the 5-membered ring to our carbonyl carbon. That's going to be an OH. And it's going to look like that. And finally, our last one. Nice, gentle elimination reaction. POCO3 is going to react with the alcohol and give a phosphate ester, chlorophosphate ester. Pyridine is going to pull off a hydrogen. We are going to get an elimination reaction, and we will make cyclohexene.
What are we doing Thursday again, Dr. Young?
We are going to do exam 3 review. In exam 3 review, we will go over reactions from chapter 9. We'll look at content from 10 and reactions from 17. All right. See you guys on Thursday. Remember, no lab. Do make sure that all of your lab reports are put up and together. On Thursday, I